Hello, welcome back to Job 300 video series for geographical data analysis for WVU. In the previous video, we looked at complete spatial randomness and the two assumptions that make it up. One of those was that any point can be found anywhere in the study area with equal likelihood. And this would lead to density-based approaches, for how we study point patterns and assess are they random or not. This video will look at two approaches using that idea, and they both build upon this idea of a quadrat-based idea. So I have here my point patterns in a very generic rectangular study area. To look at the density of the points within the study area, we basically divide that into areas. Equally sized quadrats. They're frequently small squares or rectangles, but they don't have to be rectangular. They just have to be a regular tessellation of the study area. Most often, for simplicity, it's a grid, but I have seen hexagons used as well. So I put a grid down here. In this case, pretty small, 12 grid cells. And for both of the approaches, for both of what we're doing, we will count up how many points are in each cell. Okay, so I've now counted this up. We now can have two different approaches to this. In a way, both of them use one particularly strange property of what happens to these numbers if the points are following complete spatial randomness. And they will happen to follow a particular distribution. It is, we saw earlier, in fact, when we're looking at distributions and discrete distributions, we saw the Poisson distribution. So, knowing that these will be based upon this Poisson distribution, the first approach uses a particularly curious fact about the Poisson distribution, which is that the variance of the data and the mean of the data are the same if it is under complete spatial randomness. So with this variance to mean ratio, it starts out very simple. So the variance of the number of points in the cell. So I take these 12 numbers, find the variance. Take those same 12 numbers, find the mean. Divide one by the other. If it is equal to 1, then I have complete spatial randomness. If it is less than 1, then, okay, how do I get less than 1 on this ratio? My variance is too small. My variance is smaller than it should be. How can I get the variance of the number of points per cell lower? Okay, if I get the variance of the number of points per cell down, that means they all have about the same number of points. That's how you reduce the variance. Make all the values more similar to each other. If I do that, that's going to be under what happens with an even distribution. If the points are evenly distributed, all the cells should have about the same number of points. And that drops the VMR down below 1. That means if it's greater than 1, my variance is higher. Okay, how do I get a really high variance? I have some cells with a whole lot of points and some cells that are empty or have very few points. Okay, that means I must have had a clustered distribution because those cells that have a lot of points, that's where the clusters are. Now, we still haven't, we're getting towards this idea of putting things into our statistical framework for inferential hypothesis testing. Our null distribution, our null hypothesis is going to be complete spatial randomness. Nothing interesting going on. So basically, next we want to figure out how far away from 1 do I have to get before I conclude it really is different from 1, it really is not random. It so happens that, as I said, the chi-squared, that's coming back. Here is one way it's coming back. It so happens that if I take this value, and multiply this number by 1 less than the number of cells. This n is the number of cells, not the number of points. This product, the variance to mean ratio times the number of cells minus 1, that's going to follow my a chi-squared distribution with n minus 1 degrees of freedom. So remember we had the idea of, say, the degrees of freedom, where if I'm making more predictions, I'm likely to get more error total. And so that changes the number of predictions I make, changes the shape of that distribution. That comes up here again to say, okay, the number of cells does affect this value here. I can then use this null distribution under that assumption of complete spatial randomness, under the null hypothesis, and use the same test, the same idea, the same Excel formulas to answer, is this variance to mean ratio far enough from 1 to count as a non-random distribution? That is the variance to mean ratio. There's one approach to looking at how quadrats here, this grid, can be used to generate an inferential hypothesis test of to study answer the question of, are my points random or not? There's another approach that uses these same numbers. Apologies for the slight delays. I cleaned the board. The other approach basically uses these numbers again and the Poisson distribution directly, not just working with that one particular property, but using that distribution directly. Now, with that distribution, I can say, under the null hypothesis of complete spatial randomness, given the average here, so given the overall density in the whole study area, I can say how many points, how many cells do I expect with this complete spatial randomness? I'm under the null hypothesis. I might expect, say, one cell to be completely empty, 3 to have 1, 5 to have 2, 5 to have 3. And I've already exceeded the number of cells, so I need to adjust that. 2, 4, 4. And then maybe I would expect 4 or more points to have for the remaining 2 cells. No. There's 1 left to get to 12 total. Okay, what then do I observe? None here. 1, 2, 3, 4. Four, 3, 3, and 2. Now I have an expected number of cells with no points, an expected or predicted number of cells with 1 point. a predicted number of cells with 2 points, and so on. And I have the actual values. Seeing this, hopefully you are making the connection that I can again this, again, we can use a chi-square test. We were using it to assess, are our predictions correct? Do we have good predictions? Here's what I predict under complete spatial randomness. Here's what I predict, or here's what I actually see. Do they match? And I can use chi-squared to say, is this prediction good? If my chi-squared then comes in and says, okay, you have a good set of predictions here. You have a high p-value. We're going to go with the null hypothesis. Your predictions are correct, the points are random. If it says, look, okay, if it's a low p-value, then my predictions are not that good. It's not random. And I would then conclude, in that particular case, I can only conclude it's not random. The VMR, that can tell me, by looking at that ratio, is it above 1 or below 1? I can see if I can distinguish clustered from even. In this chi-squared, for quadrats this way, I cannot distinguish clustered from even. I can only say it's random or it's not random. The way, and we'll not be doing this next thing in this class because it involves what would be really horrendous Excel formulas. There are ways to generate other predictions that are kind of assuming ways to have an even dispersion, or ways to assume you have a clustered distribution. You can use any process you want to generate your expectations, to generate your predicted values, and assess, was that correct? In this class, because it's the simplest approach, the simplest case, we will be using the assumption of randomness for this prediction, for this expected value. But where we might say the variance to mean ratio has an advantage of being able to distinguish clustered from random and clustered from even. The advantage for this approach of using the quadrats to directly generate the predicted values, its advantage is you can use other processes for those predictions, although, as I said, we're not going to be directly doing that in this class. Just be aware it is a possibility, an advantage of this particular technique for assessing point patterns. So we have seen here in this particular video the two approaches for a density-based analysis of point patterns, both of them based upon quadrats, one of them using the variance to mean ratio, the other directly using a chi-squared analysis on the quadrat counts themselves. So, as always, if you have questions, please, by all means, ask in Zoom class, send emails as you're going through the lab on this. Please ask. I know this is not always the most straightforward of topics to understand, so I encourage you to ask questions if there's anything you are confused about or anything you are stuck on. So with that, thank you for watching, and I'll see you at the next video.